Hi, welcome back. This is going to be a very special video, something that's near and dear to my heart. In today's video, we're going to be talking about the jump point search pathfinding system, otherwise known as JPS. So I find JPS to be extremely exciting, extremely interesting. I think it's a really cool idea. I have also spent, I'm a little biased, I have just spent a large amount of my PhD also working with jump point search. This is essentially one of the original ideas that even prompted me to create this channel in the first place. Why do you care about jump point search? Well, jump point search is the leading, or one of the leading, grid-based 2D or now 3D pathfinding systems. JPS really pushes forward state-of-the-art. It consistently outperforms A* by up to orders of magnitude, right? We're obtaining amazing speed-ups using this algorithm. We're improving upon the A* algorithm by, as we will see, doing this form of symmetry breaking to essentially prune entire swaths from the actual search space that we would otherwise have to consider. So we're doing some really smart reasoning. It's driven by human creativity, human crafted rule sets and pattern recognition about the way we interact and search over grids, and it's going to be state of the art. This is extremely useful for any video game developer ever working with grids, things like this. JPS has really become a staple in the literature. It has been around from 2011. It has received numerous improvements over the years, different versions, different augmentations for different domains, ways to speed it up, and it remains state-of-the-art today. So without further ado then, let's dive into what is jump point search. Well, I am first going to walk through essentially what the idea of JPS is. We're going to spend a lot of time walking through the rule sets for how we're going to be looking at what we call canonical neighbours, forced neighbours, and how that relates to the specific pruning rules that you would see if you read the original paper. Okay, so before we can get to the idea, we need to essentially describe a characteristic of search, of problem solving that's with us all the time, which makes things difficult, right? So we're in a grid map, a 3x3 grid map. I'm going to first consider this is going to be a 4-connected problem. So essentially just cardinal directions, right? There's 4 degrees of movement. Then we'll consider also a diagonal problem. From the get-go, right, we're looking at different ways we can reach the target. I could go all the way north, all the way east. I could go all the way east, all the way north. And then there's every possible permutation in between, right? We know from search, right, the idea we've already transitioned away from states to search nodes because the order of moves is important. Well, let's draw up a few of these possible paths. There's this version. There's, of course, going all the way east, then all the way north. And then we start to see, right, there are all possible permutations in between. This is a very small example, and you're already seeing that there are so many different versions of the same path. This is what we call the issue of symmetry, of symmetric equivalent paths. Every single one of these is an optimal solution. We would be okay with any of these solutions in our search space being returned to us as our final version of the path. They all have the same cost, right? It's the only difference here is that these are the permutations, the different versions of the same moves of the same cost in different orders. So this is what clogs up search. A large amount of search is really spent proving, exhausting permutations of the same moves before we're able to find and return the effective solution. In the 8-connected case with diagonals now allowed, well, this works out to be the same, right? So we have some form of diagonal moves going straight across. We have similar versions of the path, right? And there are how many symmetric versions in between, right? When are you actually taking the diagonal? And we haven't even talked about the fact that, of course, you can take the diagonal and iterate things between. All of these versions are the same. And this is even true, right, when we add in obstacles into the map. Even in these situations, we start to have all of these permutations, things that can get in our way. So all of this is just to say that symmetry is difficult, okay? Symmetric paths are wasting a lot of time. The idea behind jump point search is that we are going to be doing symmetry breaking. We have seen that one of the ways that we can improve upon the A-star algorithm is to spend additional time reasoning over the world such that we can prune, cut things off of the search tree so that we can greatly and even exponentially reduce the amount of nodes that we have to actually expand, generate, and so forth. So the idea of JPS is that we will be doing, we will prune the search space via symmetry breaking. Symmetry breaking. Okay, so how I want to discuss this is we are first going to draw up these diagrams for what are the neighborhoods of jump point search. So if you've ever looked at the JPS paper or experienced anything with this algorithm, this is, I think, where you usually start. You start seeing these neighborhoods where we've grayed out a bunch of nodes. So I'm going to do that first before I come down and then explain the mathematical, the rule-based methods for how we actually select nodes and paths to prune. But I think it's really nice having the visual example to help drive this. Okay, so this is what you would start seeing if we look at the paper. The nodes I'm coloring in are what we consider to be grayed out. These are going to be nodes that are pruned, okay? These are not nodes we have to look at all in the search space, which is quite exciting. I note as well the parent P. So these diagrams are describing essentially when we're moving from some parent P to some current node X. Okay, so X is the current node, P is the parent where we just came from, and I'm drawing that in a arrow here to indicate the movement we're taking. So essentially there's a straight move and a diagonal move. These rules, the way I'm drawing these grids, these work for all possible symmetric permutations as well. Right, so this is essentially showing this for an east move when I'm moving right, but this is the exact same if you were to just rotate the grid for either if we're moving north, west, south, okay? And similarly for our diagonal cases. So that's quite exciting. The other aspect of this is as I write these up, I will be also shading in the parent P. You never have to look at the parent P, but that one's a little bit harder, okay? So that's what I'm showing here. I will continue to move through. Okay, so here is where we begin our journey into jump point search. In the straight example, this is our bread and butter. Through some form of ways of reasoning over the world, which we'll write down here in the pruning rules themselves, we have eliminated in the entire 3x3 neighborhood around, right? Like these are the neighbors, the states, the grid cells that we can reach, right? That surround our current node. Well, when we're moving in a straight direction, I have been somehow able to throw away all other nodes except the next node in the same direction, right? So in this case, we say that there is only one canonical neighbor for node X along a straight move. So what that's going to mean when we get to actually drawing up and explaining jump point search, that is saying that JPS is going to be able to, when we're looking in a straight direction, continue to just beam, right? Look at a straight line beam all the way down the map as far as we can until, we're going to talk about it, until we find something that is interesting. This is where the terminology comes in of jumping, okay? So we are going to be able to jump in a straight line some distance until an interesting point, or we reach the edge of the map, we discover that there was nothing interesting in this direction, and we get to throw away, prune that entire path, that entire topology. This is where it starts to get exciting. So then let's look at the diagonal case. In the diagonal case, we have instead that there are 3 canonical neighbours. So maybe I should label these so that it's a bit obvious. So here there is 1, and then here there's 1, 2, 3, okay? So what we're doing here in the search space is, again, via some rule-based method. We haven't discussed how we're doing this, but we are able to reduce the branching factor This is a 8 connected problem, right? Technically, the branching factor would be 8. Technically, right, you never want to generate the node you just came from the parent, so sure, the branching factor's 7. But we are reducing that all the way down to 1, or at maximum 3, in the case of diagonals. These are the only nodes we will need in the entire search space in order to find a solution. Okay, this currently works only in the case that there is completely empty space in your map, right? So we are going to discuss this in terms of thinking about alternate paths that we could have taken, okay? So what we're going to be doing here is we're moving towards this idea that we are going to be symmetry breaking. The beauty of JPS is that, okay, you see all of these diagonal moves. Well, only one version of these is going to be the one that we keep in our search space. We are going to keep only the version of the path which has diagonals as soon as possible, okay? We call this, as we'll write down soon, diagonal first. We are employing symmetry breaking to prune all possible symmetric topologies of this path into only one canonical path, the diagonal first, right? Diagonals appear as early as they are able to in our path. This is what we're working towards. We're going to do this discussion in terms of, we're talking about, right, we have a parent P, we have our current node X, and now we're going to discuss the idea that there could be either some alternate path for every neighbor N, okay? So for every other node in this neighborhood, we're going to call one of those N as the generic sense. And we're saying that there could also be a Y, right? So to draw that up, we'll do a similar idea, right? So we have some parent P, the current node X, and we're talking about the idea of some generic neighbor N, right? So I'll do 2 of them, so there's 2 examples. Well, we're talking about either, of course, we're moving from P to X in this current situation. That's the current version of the path we're considering. Well, in order to be able to prune these nodes effectively, we have to reason over the other possible ways we could have reached the node. There are 2 versions of this path. I'm going to include this intermediate node Y, right? So there's a version of the path that is, we'll call this pi prime. This is the version of the path where we start at P, we go to some intermediate node Y, and then we get to node N, okay? Then there's pi prime prime, I guess. There's the other version of the path. Here, it would be from P directly, say, to that node N. I'm just going to call it node N here. Okay, so either it was directly adjacent to the parents and you could have reached it from the parents, or there's one extra step. All of these, right, are all the other possible paths compared to the one we're currently looking at that is going through our current node X, okay? When we return over here, well, we are going to write up the rule set as follows. Right, so I'll continue to write it in a second, but as of now, this is where we're saying, hey, we're talking about alternate versions of a path. There exists some path, right, where you're going through an intermediate node, or simply you can just step directly there. So that's me written up the full expression here for the first pruning rule. So what we're saying is that we are going to be able to color in to prune a node, completely ignore it in terms of our reasoning from our current node X, based on the idea that there was a better way to reach this path. There was a symmetrical version of the path from parent P that was, or would have been, strictly shorter, better, right, than the current version we'd be looking at. So what that means is that, in the sense that we are at some parent P, we're looking at our current node X. This is the version of the path we like here, right, Pxn. Well, we could have reached the other node, the neighbor N, through a shorter version of the path. Instead of the path with a cost of 1 plus 1, right? So P to X is 1, X to N prime is another 1. Well, there was a shorter path. It was just the diagonal directly from the parent to node N prime. In the other sense, we have the other version of the path from P to N through this intermediate node Y, okay? So in this situation, well, it is not strictly a different cost, right? So P to X and then x to n, well, that's 1 plus root 2, versus p to y, and then to n, which is root 2 plus 1. Both of these are the same costs. So up until now, with just this first rule, well, we are saying that we can essentially rule out these nodes here, right? Hey, these ones already they just strictly had a better version of the path. You would never need to go through x to find this node, right? Okay, well, we're going to then write down the second rule, which is going to convince us that we can come back and also color in these other two nodes here. So this is where our idea earlier I discussed of diagonal first is coming into play, okay? So we're saying instead there exists, again, some other version of the path. There exists a path pi prime, right, which is through our other node, our intermediate node y, that is the same length as path through x that has the diagonal move occur earlier. If we look at this example over here, from p to y to n, the diagonal move is taken first in the path, right? When we go from p to x, that's a straight move, and then we're taking the diagonal move later. Well, we're saying no, we are always going to enforce the diagonal first in this situation. So this essentially means anytime there is an equivalent cost path, but we are aware that there must exist some symmetric equivalent to this path that has a diagonal move, any diagonal move earlier than our current path, well, we are going to prune it, right? We're enforcing this symmetry breaking onto the problem, and we can prune these additional locations from our considered search space. All of this is moving towards the fact that JPS is a complete and optimal algorithm, just like A star. And the proof for how these diagonal rules, these pruning rules actually still enable us to have complete and optimal solutions, well, that's something I will walk through in terms of the force neighbours in a second, but otherwise the actual proof as well exists in the paper, and I think it will do a better version of that, right, where you can follow the math a bit more effectively. So let's then move across to the idea that now we return to forced neighbours. So all of this reasoning is fine and dandy in a world where there weren't obstacles, okay? We're talking about, of course, these moves were possible, we're able to prune them, because this move from p to y was always viable, right? We had never considered the idea that there could possibly be some obstacle right here that would actually block the move. Now, this is where things get interesting. I want to note there are two versions of jump point search. In the original paper from 2011, well, when the idea was first discussed, at this time in the type of problems we were solving and the standard notation and allowed moves, well, at the time, something called corner cutting was allowed. Okay, so what that means is in the old paper, this move here from p to x was absolutely allowed. It was a legal move even when this obstacle here was blocked. Now, for real world problems, right, we call this corner cutting. Right, this is a corner cut. In real problems, agents obviously have size, right? Your robot, your player, your agent, it has some size, even if it's not big. It is not a finite point. So when you return the path to cut across this corner, well, if these are walls, right, if your grid map, if your actual resolution of the problem you're solving is high quality, which hopefully it should be, right? In a video game, you'd only be filling in these tiles if this is close, right, to an actual obstacle. In an ideal sense, you add resolution, right, so that your grid actually well approximates the obstacles in your map. Well, then you're going to hit a wall. Your agent has size, right? It can't walk through this corner. So essentially what has changed in the literature is that we no longer allow these moves, and this has kind of become the de facto norm in all of the grid-based path path planning competitions hereafter, and a lot of our algorithms no longer allow corner cutting. Now, obviously this depends on the problem you're trying to solve and what you choose to allow as movement, but corner cutting is often disallowed in current days. And so this is where this enters the equation over here, right? This move over here, well, if there was an obstacle, this would be corner cutting. So all of this is trying to get us to say that, okay, the reasoning we've made over here in terms of canonical neighbours, well, this works absolutely fine in situations where we are in open space, okay? So we're really able to prune massive amounts of the search space when there's no obstacles, there's no interesting points. The idea behind jump point search kind of returns to the idea that we are only interested in interesting locations. We're looking for symmetrical permutations. Well, I think one of the other key ideas is, as part of this algorithm, is how we're going to be choosing the symmetry breaking is realistically the only point in time you ever need to turn in your path, right, is either going to be you're at the goal, right? So instead of passing the goal, you'll just turn and beeline straight to the goal, or there's an obstacle, right? You turn to get around a building, to get around an obstacle. These are interesting points. These will be what become jump points. So let's talk through forced neighbours in jump point search. Okay, so we obviously have the same situations over here, right? We're either moving from the parent to the current node X via a straight move or a diagonal, and we're going to look at these same situations, but then of course update them in the case that there were obstacles. So the only locations we ever need to actually reason about and to stop and to use different pruning rules than our canonical versions, well, this is when there are going to be obstacles. This is, I guess, now to distinguish between the blue, which is pruned, I'm going to color in obstacles in the pink. So all of a sudden, this is an obstacle. Okay, this node here is blocked. Well, hopefully you can see that this is not going to impact the other half of our environment here, right? All of these nodes, based on the same pruning rules before, these still are happy to get pruned. Now, different things begin to happen. Okay, so let's have a look at this top node here in the middle. In the previous example, we were able to prune this because there was always a better version of the path that reached the node from P, right? There was a diagonal move that we were allowed to take that was shorter, right? It was strictly better as pruning rule 1. We were able to ignore it. Okay, however, in this situation, the move from P to this node N, well, there's an obstacle in the way now. Assuming again the idea of no corner cutting, we're not allowed to actually walk through this. This is no longer a feasible action to take. Well, all of a sudden, the node might be important, right? So this absolutely could lead to a shortcut or a version of the actual optimal path that goes around this obstacle. And if we ignore it, if we prune it, well, we could absolutely lose completeness and optimality. This is a point that is important. It could potentially lead us to the goal. On top of that, right, it was a node that we would otherwise have pruned from the search space, and there was no other better way to reach it. This all leads us into the idea that this node here is absolutely going to need to be generated. So during search, right, we're going to be doing what is this jumping procedure, this scanning procedure. We are going to stop anytime we identify the situation. We have to stop search, and we need to essentially generate the nodes, which I'll continue to talk about, as forced or canonical neighbours, okay? So I'm drawing this in a square, right? These are the neighbours that are forced, okay? I want to convince you then that this is different because this node over here, which I'm going to label as 3 in a circle, well, that is a canonical neighbour still. So due to the same reasoning as before, well, there was no better path from P to node 3. Of course, you have to go through X to get there. Now, obviously that is giving you the spoiler that this node here is also going to be forced. How is that happening? Well, this is now, so node 1 was a forced neighbour because of pruning rule 1, okay? Well, node 2, the move from P to 1 is now disallowed, right? Which means that that was the equivalent version of the path, the equivalent cost path, that had the diagonal move earlier, yeah? But now, because there's an obstacle there, well, it means that essentially you have to go through X, right? X is now the best version of the path. It's a forced neighbor. We also have to stop, right? So we are doing our regular thing. We have the same canonical neighbor, but we need to check the two nodes that are immediately preceding the obstacle. So here I want to also point out this, okay? In the original paper, corner cutting was allowed, okay? So I also want to draw up the corner cutting rule, because this is the version of the forced neighbor that existed in that worldview. These days, I will say, we don't use this at all because this is an illegal move, but I just want to draw this up as well just so that it makes sense and you can do the comparison in your head. The difference here is that the obstacle would be next to the parent again, but this move is legal, right? This is corner cutting, so CC is allowed, okay? That is where this corresponds to. Well, in these situations, this is similarly pruned just like before, similar here, because again, this is unchanged from our previous example. And then these are canonical neighbors, just like they were before. But there is a new node just around the corner. So previously, right, the best version of the path to this node was straight from the parent. But now this move here, well, this would be forced in the other worldview. Because again, the move from X to 1 is also allowed because corner cutting is allowed. So this is the original rule set, but just note that, right, like this, moving forward in current modern era pathfinding, this is strictly disallowed, and we use the forced neighborhoods over here. Okay, so just to continue the discussion, I'm going to erase this. Okay, so I've drawn up this example over here. We're going to be working with just a standard grid map. I've drawn in a few obstacles, right? There's 4 obstacles here, and we're going to walk through how jump point search actually works, okay? So I think these examples, right, because JPS has this unbounded scanning procedure kind of built in. Well, I've tried to draw in here, right, all these dots, right, that represent that the map I've drawn is a smaller subset of a larger map, right, where essentially the map will continue in all of these directions. To keep it simple as well, just so we don't have to think about any other possible, there's no shortcuts, right? These walls over here, they will continue all the way down to the bottom of the map, right? The only version of the path we need to find is going to be one that goes this way. That doesn't impact anything, but just to keep it simple. Okay, so let's jump into the idea of jump point search. Okay, so let's dive into jump point search. What is going to be happening? Jump point search is employing these canonical and forced rule sets in order to scan across the whole map quickly to identify only jump points, right? We're going to be essentially pruning large swaths of the search space away. Instead of A star, where you stop and expand every node, right, that you find along the way, well, what we're kind of doing is we're going to be doing these look-aheads, these scans to identify if we ever actually want to stop and to generate new nodes. So we're doing additional reasoning over the map, and we're pruning parts of the map when we don't discover anything interesting. Okay, so that's really meaning that we're dramatically reducing the branching factor of the problem, and we're also very, very quickly reaching areas of importance, and we're only generating far less nodes as well along the way. So that is also reducing actually the amount of heap operations we need to do to put things into the open list, to sort them in the open list, to pop them out, things like this. So the advantage of JPS is really coming from this idea that the reasoning that we're doing is actually extremely beneficial. We reduce the heap operations that we actually need to do so much that we end up with speed ups up to orders of magnitude faster. So that's really cool. I'm going to spend a whole part of the end of this video discussing how that works implementation wise, what trick we're really doing, right? We're able these days, we're not doing this on a per node basis. You are able to read in an entire word, a 32-bit, 64-bit word, and we can jump, we can stride over that entire length at the same time. That is where the additional speed up of JPS is just so strong. Okay, so diving into jump point search. The scanning procedure is going to follow based on this. The really, really, really important one of all of this is the straight canonical directions. There was only ever one canonical neighbor, okay? So what that means is if we are continuing in a straight line, well, we never have to turn. We never have to consider anything else, right? We continue. Every time you reach a new node, you just keep looking to the next node in a straight line. This is the bread and butter of JPS. The only time we ever need to stop is if we hit the edge of the map and we can confirm, oh look, the edge of the map or an obstacle, right? And then we confirm, okay, well there was nothing interesting there at all. Or instead we find a forced neighbor, right? So if there was ever an obstacle that was blocking it, well, we'd step one and we go, oh look, this direction is forced. There could be something interesting there. I should stop and generate nodes. This is why JPS ends up being so fast. Its straights are extremely effective. Along diagonals, what we're going to be doing is every single time we step once along the diagonal, well, before we continue, we're going to need to ensure that we stop and we scan in both straight directions first, okay? Only in the case that each of these hit a wall and found nothing interesting, that is the only point then that our algorithm will go, okay, well, we can continue, we take one additional diagonal step, we do the same procedure, and we continue. So diagonals, right, are like, they have to occur first, they have this priority, but because we have to enforce this diagonal first moveset, well, we need to make sure that we scan along the straights first and we don't identify anything that's important, so we don't miss anything in the search space. The other idea, the really, really important idea here, is that from the start node is the only special node in the entire search space, okay? From the start node, we need, in order to not miss anything in the map, it is the only node we must explore all possible avenues, all possible directions from the search node. The order you do that is not directly important, but in terms of generating its children, possible successors, well, we have to look at all possible directions to jump in, okay? So all of this is to say the ordering of that is implementation-wise. Maybe you could have some heuristics to see which ones you want to look at first. You just need to make sure that when, say, you run out of nodes in a promising direction, that you would jump back and generate the rest of them. I'm going to draw them all up here exhaustively, right? Just to show you that this is how it works, regardless of, I guess it's like the worst case, right? You need to do all of them. Okay, so the straight directions are the easiest, okay? In the straight direction, I will continue looking all the way down, right? We can continue to search until we find a forced neighbor. If there was any obstacles here, ta-da. In this example, I'm saying these are the only obstacles I have. Well, this would scan all the way down till it hits a wall and then return nothing, right? There was no jump points, there's nothing to generate, and we continue to look in the next direction. We'll do the same east, okay? There was nothing interesting. Okay, here we do the same. Oh, sorry, did I say east here? We did the same west before. Here we're looking east, and here we also now hit a wall, okay? We scanned all the way across. We found no interesting obstacles above or below it to possibly force a neighbor. We hit the wall, and we again get to conclude there was nothing of interest. Now, when we move north, things become different. It's at this node here, okay? When we arrive at this current node X, this is where the symmetric version of this occurs, right? So we've moved from a parent P that was next to the obstacle, we've moved up to node X, and we've identified that this node here, this is a forced direction, okay? So what we do is we would stop and generate this node here with the possible directions it needs to look. So of course the canonical direction straight is one we need to look, the one next to the obstacle, and then this is also a potential exciting avenue. So each of these would be identified as versions of the path that we need to take, and then this absolutely would continue off into the edge of the map, off into the edge of the map, more or less. But before we continue off into the edge of the map, we would get to this point immediately off and see that again we have the same force neighbor, but for like looping around the obstacle. So this is an important aspect because there could be shortcuts, but in this kind of situation it starts to look a little silly, but that's okay. Along this diagonal, right, this is an unbounded diagonal. Note, every single time you're still doing these scans in the corresponding directions, okay? Now, yes, so we took one diagonal step here, right? Now we have to make our scans now straight directions. These will continue unbounded. They find nothing when they hit the edge. Then we get to take one additional step. Then we do more scans, right? Then we take one more step and continue. So we have this unbounded behavior. It's surprising, right, that jump point search has to look all the way to the edge of the map in these situations unless we kind of start to use things called scanning limits, jump limits, which is also a very exciting aspect. In the vanilla sense, this is unbounded, and this is still faster. Even though we're doing all this work into the wrong way, the scanning procedure is so quick that we still smash A star. So that's kind of weird. So let's continue the example. I'll start just like the non-interesting directions, right? Sure, you do this. It's blocked, so you can't continue the diagonal at all. So that's interesting. But you still need to do your one horizontal scan. Okay, all of this is going very poorly. Again, remember in this diagonal you continue to make all your horizontal scans. So you see that we have this move ordering, right? For every diagonal step, you're enforcing both straights are scanned, and then you continue. That's kind of coming from the diagonal first. We do so likewise here. Right, again, this hits a wall, so it finds nothing interesting, and you continue. Okay, so now we get to, I guess, the exciting one. We can start to see that this is an interesting direction. Note that when you discover these nodes and you generate them, you put them in your open list, all of this is operating the same as A star, okay? So your nodes are put in with an F value, right, which is dependent on the G so far. So when you're doing these scans, you have to track, right, you're incrementing your G for 1 for every single time you step, or root 2, of course, for diagonals. And then you still have the same heuristic values driving it. So when we discover multiple nodes, you still choose to prioritize which one you expand next based on the same idea as A star, which is why all of this is still such an effective search strategy. So in this case, we are going to take our first diagonal step. We look all the way up. We find nothing. It goes to the edge of the map. We look this way. Again, it hits a wall. We found nothing. So we continue again, do the same thing, but here. Okay, so we've stopped here because n prime has this force neighbor, right? Because it gets us around an obstacle. It happens to be towards the target in this location. What's quite important here is vanilla JPS operates as follows. It is doing a recursive call essentially, right? We are in a diagonal jump function. We're doing the diagonal, doing our one step at the time, and then we call a horizontal jump function. This horizontal jump function has said, we have found a jump point. Something was interesting in this direction, okay? So what ends up happening is in the original higher level function, the diagonal function, well, we actually stop and generate the node n, okay? This is what's being generated as the node that we're adding to the open list, and it is generated with the canonical directions, right? Because it didn't have force neighbors itself. When we generate this node, we say, hey, look in this direction, and look in this direction. What's quite also counterintuitive here, right, is in this vanilla version of JPS, the first version that came out, well, you see that you're actually repeating this entire horizontal scan and this entire horizontal scan, right? Both of the work, which could be unbounded all the way to the edge of the map, this is repeated, okay? So that's really interesting. This is all solved when we get to the idea of JPS-2, which is now the de facto version, the de facto implementation for JPS. And I'm going to talk about that immediately after this example. However, yeah, vanilla JPS stops. It generates node n. It does all of the same work again. So because which version, right? So it had 3 canonical directions it needs to search. That would be up to tie breaking. There's a world, right, where it chose to look in the diagonal first. And in that situation, you would then also do all of this work, right? So this would continue, ... Right, I should make that dot just to not confuse anyone. and so forth. So that work could possibly be done. Then we repeat this, then we get here, ta-da, now we generate this as a version of the path. So I'll start to draw in the full path that we find. This is the one so far. Then we continue along to node n prime. Now, n prime, what directions do we need to search in? Well, we always have its canonical continuations, right? So we could continue to look forward. This is a possible direction. This is now forced, so of course we could look in this direction. And similarly, this node was also forced. The diagonal is also possible. Again, you would have to potentially do all of that, right? Depending on your rule set, you would do all of this silly work. Okay, that's important. Nonetheless, we finally find that, hey, we can continue in this direction. We find the target. Whenever we're doing a horizontal scan, a horizontal jump, we're also tracking constantly in your loop. You have the distance I've jumped thus far, and you have the distance from node n prime to the target. So the moment you get to the actual distance that's equivalent to the target, ta-da, we know that we've reached the target. We would stop here and we would generate the target. That's important, right? So if you don't have that final aspect of this, where in your horizontal scans and your diagonal scans, you actually ensure that you're checking that the current node is the target, or we use the target distance because that's actually a more efficient method than checking the nodes themselves, well, we would potentially miss the target. So that's really important. All of this is to say, ta-da, I've drawn a whole lot of lines, but jump point search, it looked like it did a whole lot of work. It did. Again, so much of the search space we actually would have drawn all the arrows to is fully dependent on the kind of jump points that we found, right? So this was a jump point, this was a jump point, so forth. Oh, this would have also been a jump point, right? Because there was the potential version that you could get around this. So yeah, we would stop here, we would generate these. Hopefully tie-breaking means that these were looking closer, right? Their heuristic value was smaller. So these would be the nodes you expand first. These would be culled and stopped here. All of this is to say that jump point search, it might have generated any number of nodes. We don't kind of know what happened in the rest of the grid. But in the optimistic case, it would only expand 4 nodes here. Start, n prime, t, the target t. So instead of A star, right, think about A star. We would be horizontally scanning all possible nodes, right? We're stopping at every single one of these things. Along the path, this would be a node, 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 this would be a node. And every time we do this, there might be, again, we might be stopping, we're doing this stutter step, as we also have to prove that the other versions as well weren't better, right? So A star is doing this constant stuttering. It has to do all of these heap operations along the whole way. The beauty of JPS is really the jumping procedure is so powerful because our straights are so fast and we can jump really far in the map and have to generate and expand very few nodes. Let's now take a step back to talk about what is jump point search 2, okay? And then we're also going to discuss how you actually implement the scanning procedure so that we're not checking this one node at a time, all right? This one node at a time is actually completely unnecessary. We can do this really exciting stride procedure to make this extremely fast in practice. Okay, so I want to work through this example again, but under the guise of what will become JPS-2, which is just the same as JPS, but with an additional trick, right? It's just an implementation difference, really. So we are conducting search in the same way, more or less, but there is a difference now. So unlike before, where we would, in the case that there was an obstacle, right, we were continuing to scan, we found a node, right, where something is forced, yeah? Both of these nodes would be forced. Well, previously I was saying that you stop and generate this node, okay? JPS-2 is going to be doing the same procedure, but for both the diagonals and the horizontals, it actually is unbounded. You continue all the way to the end, regardless of whether you actually find a jump point along the way. But so the implementation difference then is instead of stopping and returning one jump point, the first one we find, which is why we kind of stopped here right at this previous n before we found n prime, well, we're going to be keeping instead a list of all jump points we found along the way instead, okay? So you're continuing it completely unbounded all the way as far as you can go for every horizontal, sorry, for every straight. I should really be calling them straight. So for every straight and for every diagonal. These are unbounded, and you collect all jump points you find along the way. Now, the difference here is what happens when we conduct search. So I'll draw up this example. I'm just going to draw two avenues, right? So we happen to luck out in this situation. The very first direction we looked at from the start was north. It goes all the way up to the wall, okay? However, it does absolutely generate and add to the open list the the jump point it found that had a forced neighbor. And again, the jump point, when it's generated, says that, hey, these were forced directions that I need to look in. What's interesting, right, is because we've already continued, right, we do not need to generate the continuation of north, right? We don't need to look at, again, the canonical directions, this orange direction instead. When this version of the path, right, JPS-2, well, we get to ignore that because we already would have looked in that direction. Okay, so then the next direction we'd look in is, let's say we looked northeast, okay? Well, maybe I'll do the straights just to make it look a little bit more reasonable, sure. We're going to take one step along the diagonal. We're going to, again, we still do our recursive checks in the straight directions. These continue unbounded regardless of how many jump points they find. Then we continue along. We do the same thing. However, this time we do find a jump point here, okay? So this n prime we found before, this still exists. This is generated as a jump point, but we didn't stop, right? We would have continued unbounded all the way to the wall in this direction, counting and collecting the full list of jump points we found along the way. This node here, which I should not color in, is no longer a jump point. So if we think about this situation, there are what we consider to be two types of jump points, right? So types of jump points. Type 1 is what we call intermediate. Okay, this is an intermediate jump point over here. This was a jump point that itself had no forced neighbors, right? The only reason we previously stopped at this location is because it itself had a lower order scan that found a node, another jump point, which indeed did have a forced neighbor. So I like to call these, I think the terminology didn't exist back in the original paper. They just referred to intermediate jump nodes and then all other jump nodes. I like to use, especially when we talk about JPS 3D, the idea of forced jump points, okay? So node n prime over here is a forced jump point. It had a forced neighbor. These are the important ones. Stopping here is actually unimportant. We don't even need to generate this, right? We've already looked all the way north. We've already looked all the way east. Well, the continuation, we also had to continue, right? Because we're doing this JPS-2 thing. We always do the unbounded version. So even though you collected this, you would continue this diagonal all the way and collect all jump points kind of along the way. So this jump point here, right, this intermediate jump point, well, we've already looked all the way north, we've already looked all the way east, we've already done this whole diagonal extension. There was no point to ever generate this node. If we had stopped here and not continued along the diagonal, see how if we pruned this, we could potentially lose solutions in this upper right quadrant of the map? That's why we have to do just this full unbounded procedure. There's implementation hacks, right? Like you can kind of get around this depending on how you generate the node, perhaps. You can give it just the next child would just be a continuation on the diagonal. But the standard way this is implemented really is just JPS-2 does this completely unbounded. In 2D grid maps, this just proves explicitly faster, explicitly useful. you may as well just continue it while we're already in the function call, right? Instead of having to do heap operations, come back, continue, things like this. It's just so fast that it works out, it's worthwhile. But all of this is just to say that this node here, which I colored in, well, it doesn't deserve anything. It is not special. It was an intermediate jump point. It was unneeded. We do not stop at this node. We do not generate it. We instead jump straight to N. So in this situation, the JPS path, ta-da, it only expanded 3 nodes, just the start, just N prime, and just the target T. 3 node expansions. JPS2 is the de facto implementation because it is just faster in 2D at least. But no one cares about 3D but me. So yeah, JPS2 is just really, really, really fast. It's the implementation, the base implementation we always use, because if you think about all the redundant work, right, we were saying before, the repeated scans in the straights, well, that is a lot of extra work. You do so many redundant repeated scans, so we get around that altogether simply by tracking the types of jump points, by doing this unbounded, and you only generate those that have forced neighbours. So before I continue onwards to the idea of how we're going to do this stride, I want to also just talk very briefly about some other variants of JPS that exist that are really, really important in the literature and depending on the kind of problem you're tackling. So a lot of this is leading towards, I won't discuss it in this video, but there is something called JPS-Plus, okay? JPS-Plus is the idea of JPS, but we're seeing, right, that the jump procedure here is extremely useful, right? Reasoning over the world to do such hard symmetry breaking, we really reduce the amount of nodes in our search tree, in our search space, drastically, right? And that means we can really retrieve, and this is where we're getting such excellent performance. So what's important then is JPS Plus is a cool way to adapt this to the idea of problems where, again, we have time to pre-process. So where we've seen the heuristics, right, like the CPD heuristics or differential heuristics, these problems that are very, very difficult, right, or you just need really, really, really fast paths. Well, in the case that we have some time to trade for pre-computing and storing of data such that we can speed up search, well, jump points have proved extremely useful in the literature and are really state-of-the-art. So JPS Plus is the version that essentially is going to store all jump points for every possible, again, start and target location in your world. Well, you can essentially run a JPS and you're storing all of those jump points, right, as a essentially abstraction, almost like a compression scheme, right, of the grid of the search tree. So then when you go to even use something like a CPD, or like you go to perform a real online search, you can be extracting the jump points we've already stored, which means we can really simplify the problem and we can conduct much, much faster search in scenarios where we really need a path fast. So JPS Plus has its own wealth of literature and use case applications. So that's something I just point you towards if you're interested in that. Then as well, I mean, near and dear to my heart, I have been working on JPS 3D. So essentially the translation of this idea to 3D problems, where essentially the main difficulty becomes our symmetrical permutations explode in 3D, because not only do we have 2D diagonals, but we also have 3D diagonals. So it starts to really get hard, right? Where one 3D diagonal step requires essentially a triplanar scanning procedure. One 3D diagonal has three 2D diagonals, and the straights and the planes and the subsequent straights there, so it gets quite complicated. This is, I think, really interesting. This is state-of-the-art in 3D. I think my PhD proved very few people care about 3D yet. I think it's been computationally infeasible in the past, but I think computers and CPUs now and graphics card rendering, all of this is, I think, leading towards voxel-based environments are becoming more and more accessible and potentially useful for video games and UAV navigation and all these other things. So I'm quite proud of this work. I think the ideas for the extensions of the pruning rules and the canonical enforced neighbors is really non-trivial. So I'm definitely looking forward to making a video on that as well. Finally, there is also, I guess, for connected JPS. So essentially, jump point search also works on grid maps, even if we didn't have diagonals. The same baseline ideas for the symmetry breaking and pruning works and exists. So it's a bit awkward because there's a recent publication from, I believe, someone at Google who has kind of reinvented the wheel. So they at least have provided for the first time for people in 2025, jotting down the actual rule sets for JPS for connected. But just note that this is something that has been pretty standard and used probably since around 2012. So it exists, it's just never been like formally written down until recently. But it's extremely simple. It really is just the version of this, but we have to enforce some, so for connected, we have to enforce a move ordering, okay? So now, because we can't be diagonal first, right? There's no such thing as diagonal first in a for connected grid map. We have to be either vertical first or horizontal first. So vertical first or horizontal first. Okay, so you need to essentially tie break your versions of the paths based on which, do you want all your vertical moves to come as soon as possible or all of your horizontal moves? So we have then, instead of like this diagonal, instead of the equivalent, right, where like every diagonal you do these recursive lower steps. Well, the version here is that if we're, let's work with vertical first. In a vertical first world, your horizontals go completely normally, but every time you do a vertical, well, every step along the way, you need to check your horizontals first. So to see how it's like really just the same procedure, but we just need to be more careful. Then essentially it's the same forced neighbor rule, really. But see here how this was previously just generically for straight, right? Well, this would match our horizontal first world, right? So in our horizontal first world, it's this, and you have to do these. So essentially, that matches this situation, right? So if there was an obstacle here, well then this node here is forced. Instead of forcing, obviously you don't force node 2 here because you don't have diagonals. But yeah, you force this node 1. So it works the exact same, and the rules I think are quite intuitive. But yeah, so for connected JPS absolutely exists. And then like similarly, kind of like the 3D version, there's also an 8 connected version, which is the same thing. You just need to enforce a double ordering, right? So I personally use so your z-axis before your y-axis before your x-axis, something like this. Okay, so I'm going to erase all of this again, and so that we can continue to have a look at translating this procedure instead of doing it on a single node basis. Well, how can we be doing this in some form of stride length? Okay, so let's finally get to this idea that we can reason over the world, not in single steps, but we can apply the symmetry breaking procedure really, really effectively through what we're going to be showing is just a series of bit operations. We are able to take a stride of some set length, some word length, because we can abuse the fact of how our computers actually store the maps. So I have drawn up a little subset of a map here, right? I've given it a bit of a coordinate system so we can talk about it. We are moving from parent P to node X, right? We know, of course, you'd have to both look in the vertical direction, continue along the diagonal, as well as have this horizontal scan. So in this problem, we are going to be looking at the, right, again, this is all, it's all symmetric. We're going to be looking at this little horizontal scan and walking through how we can essentially do this in some very, very simple bit shift operators in order to find when we need to stop extremely quickly. So I'm going to continue this all the way. We are going to be talking about this as if our word length is a byte, right? So we have 8 steps here, okay? Now, know that this whole discussion works just with the 8 because it's easier to draw the example, to talk about the example. Well, the beauty of modern computing, right, is that our operating software these days uses either 32 or 64-bit words. So that's really exciting for JPS because we get to take whatever stride length you can essentially fit in. So we can work with either 32-bit steps or 64-bit steps. Maybe you have to tune which one of those you prefer based on, hey, do we usually find jump points within 32? Well, then it wouldn't be worth doing the bit operation for the whole thing. But that's really up in the air. The standard implementation now, just because 64 has become so much more common on modern machines, I think the standard JPS starts to move towards just reading in 64 because it's extremely quick. Okay, so let's discuss then what are we even looking at here. This is a subset of a map, okay? We obviously have 3 obstacles in here and everything else is traversable. What we're going to be doing, this is called block-based reasoning. Block-based reasoning. Right. Block-based reasoning is exploiting the idea that our maps are stored in contiguous rows. The bytes, the bits that correspond to obstacles or free cells, well, those rows are stored together in working memory. That is exciting because it allows us to start reading in that data, right, fitting that within a byte or a word, right? And now we can start to do operations to check and to find very quickly the operations we're looking for. So I want to convince you very quickly that I could read in a byte around our position X, okay? So we read in that there are 1, 2, 3, 4, 5. There are 5 free positions, right? So 0s, 0, 0, 0, 0. There are 5 positions that are completely free, they're absolutely traversable. There is an obstacle over here on the next spot, and then of course there's also 2 free locations thereafter. This is where we're starting. Now what we're going to be doing in order to be checking, right? So when we're checking for false neighbours, you're looking for an obstacle either above P or below P in whatever like symmetric equivalent is, right? So we're going to be trying to check, right, intuitively, for positions that are free that follow an obstacle in either the row above or the row below. That's where this is all leading. So we are going to also define bytes, words, to have a look at the row above and the row below. So the row above is happily all 0s. There's no obstacles, so that's completely fine. Okay, but the bottom one is a bit more interesting. So here we would have 2 0s, 2 1s, and the rest is 0s. Okay, so we're left with this. Now let's talk about how we're going to use simple bit shifting operators to start comparing these things extremely quickly with our machine. Okay, so we're really interested in 2 cases, right? So before I distinguished the idea of going off the edge of the map as well as hitting a wall as 2 separate ideas, but realistically, right, both of these situations are just dead ends, yeah? You're hitting something, which means we've run out of areas to look at and we found nothing important thus far. So we consider these to both be dead ends. And to also make this quite easy to do, right, so we don't have to worry about walking off the edge of the map, in our standard JPS implementation, we actually just pad the map, right? It's really that simple. We'll add in essentially some amount of padding to the end of the row and to the beginning of the row, as well as in some set number of rows at the beginning and end of the table, right? So you're essentially just padding out blocked areas that do correspond with essentially the modulus of how, essentially just how many cells remaining would there be so that it fits in nice words. So if our word size was 8 here, right, we would simply check that we could, within the row, right, you see how many words there are that fit in it. So here it's 8, and then here you'd be looking at just 2 more. So we'd fit in 6, right? We'd fit in 6 additional obstacles at the length of the row, such that when we read this data in, it nicely fits and we can immediately just get for free that this is a dead end, and we don't have to worry with like reading over the edge of memory and so forth. So in terms of dead ends, a position BI is a dead end if essentially, right, we're looking for an area where it was free and then it is no longer free, the immediate bit afterwards, right? So if BI was free, but BI plus 1 is not. Okay, so that's extremely simple. Dead ends are extremely easy to find. The beauty of this, right, is that we're doing all these binary bit operations. Well, our computers have extremely fast and convenient methods already available to you. We're writing this in C++ because its performance is extremely important in pathfinding, so we're trying to get bare bones algorithms. So unlike something in Python, you might just have to do this manually, but in C++, we're able to leverage just the inbuilt operators for essentially it's FFS and CLZ. These are these inbuilt operators that it's able to essentially return the first set, is what FFS is. So we're identifying extremely quickly where the first one location is, where the leading one is, right? Essentially finding the directly for us, the first obstacle, the first dead end. So that is nice and simple. That's a bit boring. Then we look at the more exciting version of this, right, which is forced neighbours. Okay, so for forced neighbours, what we're going to be looking for, so force of some byte b. Okay, so what we're doing here is we are shifting across the entire byte by 1. Okay, that is what this double arrow symbol means in your computer instructions. And then you do a logical AND with the inverse of b, right, where you just flip each of the bits. So I think that this is quite confusing, right? So let's jump over here where I've drawn up an example, and we can talk through this and understand what each of these components actually mean and what the essentially the bit operation is that we're performing. So I've drawn up here the original grid, right, that corresponds to the row below, okay? So we're testing the row below for any jump points. We see that it has the same 2 obstacles, and I've converted this into the byte representation as we already saw, where we have these leading 2 zeros, we have the 1s for our 2 obstacles, and then another series of free space. So what we're looking for here is for the right shift operator, okay? So just as a quick aside, I'm using the right shift operator in this example, right? Because I think this matches what we're looking at visually better. The original paper used a left shift operator. The only difference there is that it really depends on whether you're assuming that your data is stored in either big endian or little endian, which just means which direction are your most significant bits stored. I think it makes more sense to work through this example using the right shift operator. So let's jump back in and continue that. So what we do is we take this as the rightmost bit, right? It gets shoved off the edge and lost. Then we take each other bit and we shift it across to the right. So this 0 over here becomes here. Then we have our remaining 3 zeros, right? But now this 1 is moved across, okay? Then we have our other 2 zeros. Now what happened, right, is we have this new location coming over from the right. Well, essentially how we deal with this is that, of course, this is not information we had. This is just a 0. So that's just how the right shift operator works. Now we're looking for the inverse. We're also defining the inverse, right? So we're just flipping each of the bits in the original byte. So these 2 zeros become 1s, right? The 2 1s become 0s, and then the 0s become 1s. Okay, so what we're finally looking for, this final big expression that we're trying to evaluate to check if there are any forced neighbours. Well, realistically, right from the beginning, in this example, what we're trying to find is that when we're doing left to right traversal, left to right, the forced neighbour would appear here, right? We're trying to check that, hey, this location was blocked, the one after it is free. That corresponds to a forced neighbour in this direction, right? If we flipped the whole ordering of this, well, we'd have to kind of flip all of our logic. So we'd be doing left shift operators if we're going the other way. We would be using, instead of the FFS instruction, we would be using the CLZ. So there's like this inverse kind of operations going on here. I think it's pretty easy to convince yourself how that works. Here, what we're finally doing is we're doing an AND operator between these two bytes. So an AND operator is checking each of the individual elements, and it is only true if both of them are true, right? If A and B are true. So 0 and 1 becomes 0. 0 and 1 becomes 0. 0 and 0 is still false. True and false is false. Finally, we have two true values together, right? So yes, both of them were true. Ta-da! AND is still true. Then convince yourself that in the remaining elements, they were also zeros. Okay, so we've identified here one location that was important. One location has been found, we've identified as a forced neighbor. This is in the 5th position. Well, let's convince ourselves. 1, 2, 3, 4, 5. Ta-da, we have correctly identified our forced neighbor. Okay, so returning then back to the bottom here, all of this is essentially to say that we are able to identify forced neighbors this way, but there are, there's a row above and there's a row below. So the beauty of all of this is that we are absolutely able to do this work at the same time, right? Using simply the binary OR operator now as well. So when you're checking whether some byte X has any forced neighbors, right? So forced of B to the X, well, this is just forced of B up or forced of B down, okay? And then the very final version of this as well is if we are just simply checking, was there a dead end or was there a forced neighbor at all? And so I've just erased that because then there's the final version of this, right? So we can finally do one step. If I'm just trying to define a new byte, byte S, right? So stop, S is for stop. Where do we need to stop? This is including both dead ends and forced neighbors. All of this is a single line of code. We're just essentially doing the OR operator on forced down, forced up, and again, coming from the idea of dead ends, it's just Bx itself, because just Bx itself will tell you when there is an obstacle, right, when there's a dead end. Okay, so you'd be looking at BS, you're checking if BS does not equal 0, right, if there's any non-zero bits in the entire word, that means we're going to have to stop. We don't continue to recurse our stride, our look ahead, our jumping. Then you have one final job. You need to essentially check 3 things. You have to identify again forced neighbors, dead ends, and the goal. So in that regard, you already have, the distance, right, for a dead end. You know the distance until the first obstacle. If the first non-zero, like the leading non-zero bit found in BS, well, if that corresponded to a jump point, it's a valid jump point. However, if the jump point occurred after the obstacle, right, well, of course, it was unreachable. It is a dead end. We do not return a valid jump point. And then the final aspect of all of this is you, again, need to make sure that we don't step past the goal, okay? So in the world that there was no obstacle here, and this was a goal, well, you would have computed the distance from X to the goal, and you make sure that the distance we would be trying to step in our stride is not greater than the goal. If it is, simply stop at the goal, and hopefully we're going to expand the goal and we'll be done. And so the beauty of all of this is that jump point search is able to not only use this on a single basis, we are able to use block-based reasoning to apply and very quickly identify in the map based on exploiting the idea that the map is stored in contiguous sets of bytes. That's awesome for us, right? We can check just using very simple binary operators when we have these dead ends, when we have these jump points. And that means that our straight scans, right, so both our vertical and our horizontals, these are extremely quick. This is where the speed ups of JPS come from, on top of the heap operations we're saving. But the downside is that our diagonal steps are still very slow, okay? So we're not storing some diagonally adjacent version of the map. So in the code, right, you actually have a for loop that's manually incrementing the x and y values appropriately to take each diagonal step. Then you recursively call your straight functions, and that's the speedy version of this, right? So you're scanning in straights is extremely quickly. There's only one canonical neighbor. Diagonals, you kind of have to take this slower approach. So in conclusion, jump point search is an extremely interesting and exciting idea that leverages symmetry breaking to massively improve upon the A-star algorithm and massively speed up search. This is state-of-the-art pathfinding in 2D, and the beauty of these ideas is that this symmetry breaking technique is often orthogonal to other speed-up techniques in the literature, and by that I just mean essentially that. The speed-ups we're actually obtaining through JPS are oftentimes actually able to be used with other versions for other ways of improving the speed of our algorithms, and so that is quite exciting. Jump point search is near and dear to my heart. I think it has not existed much on the internet. Here are the rules. Here's the extensive version of how it works. I highly recommend looking up the paper. This is, if you are a game developer, this is the holy grail. You should absolutely look at implementing jump point search. The implementation is not as hard as you might think, and I will also link to the Warthog pathfinding library where this is implemented by the original authors and is a really good ground base for how to continue to extend it yourself for your own projects. So thank you for watching, and please join me when I discuss other state-of-the-art algorithms in the literature. Cheers.